So this is a talk about how we translate Dart to efficient JavaScript. And I hope you guys are interested in either JavaScript or compilers, because this is the two topics that I'll be mentioning. That, of course, plus some Dart. So first of all, as I said, my name is Kasper. I work as a software engineer at Google. I've done a lot of programming language projects. I used to do embedded Smalltalk, which was a lot of fun, but apparently nobody really likes a programming language that doesn't have curly braces, so we ended up doing a V8 instead, which is a JavaScript engine that we built at Google that got included in Google Chrome that we shipped like 4 years ago. And we had quite a lot of success with that small project, and it's now being used not only in Chrome but also in Node.js and other setups. And I think we've helped push the limits on what you can do with JavaScript, which really brings me to the next bullet up there, Dart. Dart is a language that I helped co-design. It's a new structured programming language for the web. And one of the core features of it is that it compiles to JavaScript. So it's compatible with the open web. You can use it in any modern browser today. So I'll give you an ultra quick introduction to Dart, but I'll focus mostly on the compilation and the compilation of Dart to JavaScript. So Dart is an unsurprising object-oriented programming language. It has classes with single inheritance. It has implied interfaces for those classes, so you have something that resembles interface from other languages. And it has a very familiar syntax. The familiarity of the syntax is very important to us. It's very hard to come up with a new programming language and make it a success, so you need to make it look appealing to people, and a big part of that is making it look familiar. There are some novelties in there and some things that we really very happy with, like optional static type annotations that allow you to, in the places where it makes sense for you, document the intent of fields and variables by giving them a static type. You don't have to do it, but you can. It's a very powerful thing. I'm not going to spend a ton of time on that in this presentation, but it's a very powerful feature of the platform that you should probably try it out if you haven't already. There's a tiny bit of code here on this slide that just gives you a feel for what Dart is. This is actually without any class or anything. It just uses a top-level method called main, and it has the familiar C-based control structures like for loops, variables introduced with a prefixed type like int I equals 99, and some print statements with some string interpolation expressions that just make it easier to work with strings. Hopefully this doesn't look too scary to you guys. It'll get worse in the presentation going forward, but hopefully this is sort of somewhat familiar to most of you. So this is how we execute and deploy Dart code. So you write your Dart code in your favorite editor, and you write it as source code. Then you have two options. Either you run it directly on the virtual machine. That's the rightmost part, the Dart virtual machine, which is either embedded in a browser. We have custom builds of Chromium, the source base for Chrome, that has this native VM enabled in it. So there's no compilation step, you just run it there, which is really nice. You can even run it standalone as a server-side scripting language. It's a very nice feature. On the other hand, if you're in a situation where being compatible with existing browsers out there is really important to you, you can also use the Dart-to-JavaScript compiler that we've built to translate your Dart code to JavaScript that runs on any modern browser. This is a very simple picture, and there are other tools involved too, but you have these two options. Either you compile to JavaScript and run that in an existing browser, or you run the code without compiling it, just directly on a native VM. So Dart-to-JavaScript compilation is very important to us. It's very important for us to support Dart across all modern browsers. So we regularly test on both Chrome, Firefox, IE, and Safari. Opera is just around the corner for us. So we want to make sure that no matter what kind of modern browser user is using, you can run Dart code in that browser through translation. So this actually means that the Dart VM is an optional component. You don't have to use it. It's very cool and it's very fast, but you don't have to use it. We're not trying to force you into using that piece of technology. So being able to compile to JavaScript is very important. Of course, it's also important that we can generate efficient and compact JavaScript. that should go without saying. The team that I'm a member of, we take great pride in performance, and it's really what drives us. So being able to compile to something that's efficient to run and is fairly compact is certainly something we care a lot about. The third thing is that we want this translation to implement the proper Dart semantics. When translating to JavaScript, there are certain things that you could decide to perhaps not do. Like JavaScript allows you to pass any number of arguments to your functions. You can pass too few, or you can pass too many. Dart doesn't allow that, so we have to make sure that when we translate Dart to JavaScript, we keep that same semantics, that you cannot pass too many or too few arguments to a function. We want it to be more strict and more, less. There's no implicit coercions to numbers and strings in Dart, so whenever the underlying JavaScript platform would do those things for you, we have to make sure that it doesn't affect the semantics. I'll give you some examples on what that really does to the code and what we have to guard against, essentially, in a few moments. The other big thing is JavaScript as a language doesn't have the notion of checking indexes when you access arrays and lists. So it's essentially anything goes. If you pass in an index that's not within range, you just get undefined out. That's not the Dart semantics. We actually want you to get an exception if you try to go outside the bounds of a list and an array. So here's a small example, more Dart code. It has a main method, and it creates 2 points. In this case, I decided not to put static type annotations on the P and Q variables. So this looks very much like JavaScript code. It computes 2 points, as I said, P and Q, by calling the constructors of those things, and then it computes the distance from P to Q. So how does this look if we translate that to JavaScript? Well, it's pretty close. This is actually the JavaScript we generate for that. So there's a main method. Well, in this case, it's a JavaScript function assigned to the main property of a dollar object that I'll tell you a bit about later. And within that function body, the code is more or less what you would expect. There's 2 constructor calls. In this case, we're not using new right here. It's actually hidden behind this factory call to the point factory. But the distance to call is also a bit special in that it has a $1 suffix at the end, which is our way of making sure that the distance to method gets exactly 1 argument. But if you take a step back and maybe sort of halfway close your eyes, this will look more or less like the slide I showed you before. It's very, very close to like a one-to-one translation. So I mentioned that these top-level functions, and in this case the main method, is put on this dollar object. Why do we do that? So JavaScript has a notion of global functions, so you could just stuff them on the global object instead. Well, it turns out that putting too much stuff on the global object is kind of annoying if you want any kind of modularity in your code. So if you ever want to mix in code from some other place, you may have conflicts on this one global object. So instead of throwing things in the global object, we actually go for putting them in a smaller object, and we just have this shorthand notation for accessing that called the dollar thing. It's actually part of our isolate story, and isolates are our way of running multiple independent units on the same JavaScript VM. So there, every single isolate would have its own sort of isolate object represented by this dollar thing. So top-level functions, constructors, all those things, they just go into that one namespace instead. The compiler emits that for us. So the method calls were just simple JavaScript function calls, except that we translate and encode the arity of the call in the name of the method that we're calling. This is also done to help us support something like a named optional argument, which is a feature of the platform. And essentially, we're just trying to make sure that the stricter semantics we have of Dart is kept when we compile to JavaScript. So the Dart compiler is kind of a sophisticated piece of code at this point. We started out with a somewhat simple implementation of the Dart compiler, and it generated quite a lot of code, and it took a long time to generate that amount of code. And it turned out that we were actually compiling lots of pieces of the code that weren't used at all. So we decided to try to tackle that from the ground up through a mechanism we call tree shaking. Think of all your code as sort of a tree and or a sort of a weird graph of dependencies between the different functions and the classes, and think of the dependency tree that you can get of like grabbing hold of the main method, the one entry point you know is there, and just shaking it until all the things that you don't need drops out. That's what we think of when we say tree shaking. It's actually a term from at least the old Smalltalk systems that we've just kept in the mix here. It has 3 stages, this tree shaking. It starts out on the very right, that is the left, by reading in the main file, which may have imports of other files and may have a source file that needs to be read from either the web or a local file system. We just read them in, and we do a very quick sort of it's a bit of a hacky parsing of this thing. We don't look at method bodies. We don't look at all the concepts that we don't really need to look at. We just want to figure out what are all the bits and pieces that we need to bring in, all the source pieces. Once we have that brought in, we'll actually start the middle phase, which is the resolving phase, where we figure out what every name refers to. And the way we start that is actually just by putting this main method of the entry point into a resolution, a resolver queue, and then we do a full parse of that. When we have a full parse of that, we will know more about the method body there. So if main refers to something like the point constructor, we'll actually go back from the resolver and feed that into the resolver queue and say, we actually need those constructors too. Because you don't have full type system in a system like Dart, it's a sort of a conservative approach here. So if you see a call to a method called foo on something you don't really know what is, you just have to make sure that you put in all the foo methods that could potentially be called. So this is an approximation of the set of things that you need. It turns out it actually works pretty well. There's a lot of things we don't have to deal with in the common case, but we do tend to get a bit too much information, or a bit too many methods involved in that way. So this queue actually knows about classes we know that are instantiated. It knows about which method names are in use, and it knows a bit about type information for receivers. Most typically because you've called methods only on the this object where you know something about the enclosing class. Once we've done the resolution, we know something about which names bind to which things. We actually feed that into another queue, which is the compilation queue. And we start over. We put in the main method there, and we build that, essentially again, that same queue. The reason why we do that is that the code generator actually has an optimization phase that propagates type information through this through the intermediate representations we have in play. So sometimes we have more type information there. So whereas in the resolver we might know that foo is called on something, in the code generator we actually may know something about what it is called on. This is very abstract, but the end result is that we end up diet parsing a whole lot. We resolve and parse slightly less than that, and we actually compile and generate JavaScript code for a subset of that. The net result is that something like a hello world example compiles to a very, very short amount of JavaScript code, and of course, the more dependencies and the more stuff you import from other libraries and you include that way, the bigger your application will get. So it's more like a pay-as-you-go rather than anything else. So when compiling Dart to JavaScript, there are some language challenges that I briefly mentioned before. I just want to dive into some of those. One of the big ones is that Dart has support for user-definable operators. So you could say that on my class, my vector class that I invented, I want to support the plus operation. So you can add these vectors together, for instance. JavaScript has this notion of implicitly converting plus inputs to numbers. So if you do a plus somewhere, it's either converted to a number or string, the two inputs, depending on, well, the inputs. But there's no way you can make that plus, like the JavaScript plus, essentially do like a more high-level plus operation on vectors for you. So you cannot use JavaScript plus to implement Dart plus in the general case. It just doesn't work. The other way to do it, like the simple way, is just to say, whenever we see a plus in Dart code, we'll just call a method on the left-hand side. And we actually tried doing that. Just add method calls for all arithmetic operations. Turns out it's just too slow. At the sort of the lowest part of the slide here, I've showed how you could do that by just adding a add method or a sub method to the number prototype, and that actually allows you to call the add method or the sub method on numbers. So it actually works. The problem is this method is very slow, and the reason why it's very slow, well, one of the reasons why it's very slow is that inside this JavaScript function, that this reference in there is actually a boxed object. So when you call the add method on, say, on the integer 1, the JavaScript engine actually has to go ahead and wrap that integer 1 in a new object and bind this to that object before it can call that method, which gives you the overhead of allocating on every single arithmetic operation, which is just painfully slow. In strict mode, that's not the case, but it's, we didn't want to use strict mode to make this. We didn't want to rely on strict mode for making our stuff work and be efficient. So our solution is actually to figure out when we can use JavaScript Plus, when it's safe to use it, when it has the right semantics for us, and we do that by tracking types in the compiler. So if we know something about the operands, if we know you're operating on numbers, it's safe to use a JavaScript Plus for that. The other big thing is range checking. So JavaScript has no notion of out-of-bounds access, and all keys are essentially treated as strings. I'm not sure that all people that actually work with JavaScript are sort of aware of this, that they're actually working in a language that allows them to, well, that actually doesn't really help them in defining arrays of a certain size and checking that you're accessing stuff within that. So in Dart, we've decided to fix this problem that JavaScript has of sort of keep on trucking mentality, that just anything goes and we'll just deal with it later, by inserting these explicit index checks unless we can prove that we don't need them. So that means that whenever you access an element of an array in Dart code, in the JavaScript code translated from that, you will see explicit checks that you're within the range of that, which is something like comparing against 0 and the length and stuff. I'll show you that code in a moment. So here's a nice piece of Dart code that will allow me to tell you a bit about these optimizations here. So can everybody see this code at the back too? Otherwise, you'll have to come closer. So this is, again, Dart code. As a main method, it creates a list. There's a sum variable and just runs through the elements of the list from 0 to almost up to the length, and just adds them together and prints the result. Fairly simple code. When we compile this to JavaScript code, it's not a one-to-one translation anymore. So you can probably recognize some things in there. The list is unchanged. The for loop looks a bit bigger. But the biggest thing is really that before accessing the list elements, we actually insert an explicit check, which is the if I less than 0 or I greater than the length of the list, greater than equal, throw this index out of range exception. That's the Winnie the Pooh reference, I order. When we've done that check, it's perfectly safe to access the list, as a JavaScript array actually, which makes it reasonably fast, but it's kind of annoying that we have to insert this check just because JavaScript doesn't do that for us. But to preserve the right Dart semantics, we've decided to do that. The other big thing here is that whenever you're adding things together, to be able to use JavaScript Plus, you have to make sure that the stuff you're operating on is actually numbers. So we actually check that stuff we read from the list is a number before we operate on it. If it's not a number, we will actually throw an illegal argument exception instead. You can see we've done some amount of shortening the code here by using shorter names just to, well, for one thing, make it fit on the slide. And the other thing is, of course, that people care about code size. So if we insert these checks everywhere in their code, we have to make sure that that doesn't take up too much space either. One thing I probably should mention here is that we're actually clever enough to realize that the list, that length doesn't change in this loop. So we hoist that out of the loop and read it before entering the loop only once. And actually, if I were to recompile this today, the length check would actually go away because we've implemented some array bounds check elimination, because in this case it's simple enough that we actually know we're within bounds. So this is actually kind of wrong to show you guys, but it's just nice to show you that you might see stuff like this in your code if you compile and look at the output. Another thing that is fairly common in Dart is to write classes. So we see a lot of people in JavaScript using something that resembles classes by having these patterns that they use for setting up a constructor function and adding a bunch of methods to the prototype of it, and they have different patterns. And some frameworks support different patterns, and it's certainly the case that even when programming in JavaScript, there's a lot of sort of ad hoc class definitions floating around. In Dart, it's even more so. People write a lot of classes, and that means that you have a lot of the like the boilerplate for creating instances of classes and accessing the fields of classes that you need to figure out how to produce. So we've decided to go for like using a simple helper function for setting up this system and just generate most of this boilerplate dynamically at runtime using the fact that JavaScript is a dynamic platform that can actually, you can inject and generate new code into at runtime. So it looks like this. The point class I showed you before, well, I used before, would actually compile to something like this. This is JavaScript code. It looks a bit foreign. It has an assignment to a point property on the islet object, and it has a method, and it has a superclass definition. So we hack it all into one object literal, which is fairly compact. The empty string up there denotes the fields that we have. So we say that all points have an X and a Y field. Nowhere here do we have to write the actual constructor function for the point, because that is actually computed at runtime from this list of field definitions and the superclass definition that is object. The methods, however, are just put in here like ordinary properties on this object. So the distance2 method with the $1 arity encoding stuff looks more or less like the JavaScript function you would expect, but the stuff around it is actually a compact way of introducing classes. So we take this list of fields like X, Y, and we turn it into code like function point X, Y, this is the X assignment, all that stuff, all that boilerplate. We generate that for you at runtime. Of course, you only have to do this once with the point class. Once it's in play, you don't have to do it anymore, but it means that the code you transfer to your clients is smaller, and it only sort of expands in size when it's actually run on the client side. So we get these helpers generated for us by the system. We actually also allow you to have field lists that have sort of slightly more advanced annotations. So you can have a question mark or an assignment thing in the field name, and that's just our way of figuring out if we need to introduce a setter or a getter or a combination of the two for those fields. So this is just a compact way of doing it. Nice thing is, if you look at the JavaScript output that we generate, it looks like we preserve the class structure pretty well. So I hope you're all familiar with closures in JavaScript at least. So in Dart, we do have closure support. So you can have these function expressions floating around that takes arguments and produces values. And our closures actually support named arguments, and they also have to be checked in the sense that if you pass too many arguments to them or too few, we want to catch that. So initially, we wanted to try to compile a Dart closure to a JavaScript closure. It turns out that it's kind of painful because the JavaScript closure is something you can just invoke. And there has no notion of checking how many arguments you pass it, at least no cheap way of doing it. And it just somehow it's hard to figure out a way of making this fit really nicely together. So at some point we realized that allocating small JavaScript objects is actually very cheap. It's faster than allocating closures in many cases, at least on certain VMs. And we found that even with up to like 6 or 7 fields, you can create an object of a simple JavaScript object in the same amount of time as you can create, and the same amount of space as you can create a closure. So we talked about actually just using objects for representing the Dart closures. So we actually implemented this, and it turned out so nice that this is what we kept in the system. So we treat closures as instances of closure classes. So essentially in our model, a closure is just some object that has support for being invoked. It has these call methods. We use instance fields in these closure classes to represent the variables that you capture from your scope, and we use methods on these closure classes to implement the calling conventions that we need. This is a bit abstract. I'll just show you. Here's Dart code. There's a list. I run through the list, and for every element in the list, I will get the index. This is actually kind of weird code, but anyway, what you have in the middle of it here is actually a closure that takes a parameter each and produces the result of calling list.indexOf with that each thing. And at the end, we print everything. So this is very short, concise syntax for doing map operations on a list. And what we compile it to is actually this. At the bottom, you can see this closure class. It's a class like any other. It's like the point thing I showed you before. It has a single instance field called list, and it has a method called call $1, which is what we need to, the action we need to invoke when we're invoking this closure with one argument. So in there, you actually see the code for the closure. At the use side, where we allocate a new closure and pass it to the map operation, what you have there is actually a standard allocation call that creates a new closure. So it's fairly simple that way. The biggest downside is that it really rips apart the body of the closure and puts it in a different place in the code. So essentially, this splitting it out in two different parts in the output is sometimes a bit harder when you have to debug because you end up jumping between different places. But it's very nice for compiling and having a unified model of how we deal with closures and classes. So one thing that's probably worth mentioning here is that it might be a small detail for some, but it's actually kind of important that at the return $indexOf, we're not calling indexOf on the list. We're actually passing the list as the first argument. And this is a general thing. In our system, we've decided not to do what people usually refer to as monkey patching of the core classes. So numbers, arrays, and strings of JavaScript, we're not adding a ton of new functionality on them. We actually prefer to keep that on the side in this isolate object, and we just invoke this isolate object with this as the first parameter instead, because then you don't have to actually add things to these things. Again, this is a way of trying to avoid clashing name clashes in these common objects. So I showed you a lot of code already, and now I want to tell you a bit about how we actually go about generating this code. So as I said, the Dart compiler is kind of a sophisticated beast. It's a fairly sort of classic compiler, except for the tree shaking, perhaps. And it starts with building syntax trees for the Dart code. Syntax trees are like a very simple representation of your source code, and it could look something like this for a simple plus expression. You have a plus node, and you have a 2 and a 3 node hanging below it. So we go through a stage that we call SSA graph building that actually constructs an intermediate representation based on an SSA form. SSA form is probably not familiar to all of you, so I'll just give you a brief sort of heads up on what that is. So the SSA form is static single assignment form. So it's a classic compiler intermediate representation form that people have used over the last maybe 20 years to with good results for dealing with the data flow analysis part of the compiler. So what we actually translate a syntax tree like the one above to a flattened out representation that just have essentially instructions on what the resulting code needs to do, just lined out in a sequence. So we have like constant 2, constant 3, and then a call that adds these two things together. So this is a sort of a kind of a high-level intermediate representation that we use, and the nice thing is that it allows us for certain optimizations that I'll cover later. Once we've built this thing, we run through a code generator, and we end up with a syntax tree that represents the JavaScript code instead, that can then be pre-printed and emitted, and that's what you see. So the intermediate representation that we have for the SSA form is a graph of basic blocks, essentially. If you take the code on the left, it has an if with an else in there, so it has two different branches that are possible, and has some merging. It actually compiles to something that looks more or less like what I have on the right there. It has 4 basic blocks. There's the entry one that everything goes through, and at some point inside that basic block, there's a split. Either you go to the left or you go to the right, depending on the value of x and y. So the basic block on the left will call print of x, and the basic block on the right will call print of y. and then they will join forces again at the return side, and we'll end up returning either x or y depending on if we executed B1 or B2. So the trick with static single assignment form is that you end up having these, we call them phi nodes in the graph. They are nodes that are sort of explicitly merging two possible values from two different points in the code. The static single assignment property is that every single value produced in this thing is only produced in one place. So for instance, when you go to B3, we have to figure out if the return value that we need to produce is from T0 or T1. This is a classic optimization form, and it allows us to do optimizations on it. And of course, the tricky part is finding a nice way of going from this rather abstract form back into JavaScript that looks reasonable. When we optimize, it's often very important for us to have a notion of dominated tree, where a dominated tree is really, it's a tree of the basic blocks that you have in the graph, where you know something about which blocks are always guaranteed to be executed before other blocks. So in this case, you're not guaranteed that B1 is executed before B3. You're not guaranteed that B2 is executed before B3. But you know for all the blocks up there that are not B0, that B0 will have been executed and run to completion before you start running B1, B2, or B3. This actually allows you to start propagating information that you find in B0 to the nodes in B1, B2, and B3. So we use a lot of dominant tree traversals in the optimizing phase of the compiler. So the kind of optimization that we do is listed here. Like we do a lot of type propagation. So we'll know that that we can generate much better code if we know something about the types of the operands involved. So we propagate types through this SSA form, and that gives us a lot of information that helps us optimize. We also do a lot of function inlining. When we know enough about the methods that we are calling, we can actually inline the bodies of them at the call side, which makes certain things much faster. Another optimization we do is global value numbering, which I'll cover in more detail. But I already showed you a loop invariant code motion phase that moved this length accessor from the list axis outside the loop. So these are all classic optimizations. It's not something we've invented for Dart-to-JS, but we've just made sure that the compiler has enough structure to support these kind of optimizations. So I want to give you a feel for what kind of compilation tricks we play here. So I want to spend some time on one of the optimizations, global value numbering. So global value numbering is a way of essentially replacing instructions with other instructions when we know they're going to do the same thing. So getting rid of common sub-expressions is another way of formulating it. So for global value numbering, we say that two instructions are the same if they perform the same operation on the same inputs. So clearly, sometimes executing an instruction can have side effects that may affect other instructions. But in general, if you already computed a value and you haven't been affected by any side effects going forward, you don't have to recompute that value. That's essentially global value numbering. So here's a simple example of that. Here's a small Dart method called wat that produces the result of adding 1 to x and summing that with adding 1 to x. There's some refactoring that should have been done on that code level already then. But if you haven't done that, you get an SSA form that looks something like this. There are no branches here, so it's very simple. You have T0, which is the x parameter. You have T1, which is a constant 1, and then you add them together with a call that adds T1 and T0 and T1 produce a value. And then you more or less do the same thing afterwards. As you can see here, we have different calls to plus. You have 3 different calls to plus, and it would be nice to cut that down a bit. So global value numbering will actually run through this code and figure out that the constant 1 introduced at T3 is actually something we've seen before. So we can get rid of that and replace that one. So at this point, my point was that the T3 one we can get rid of, and we can replace the use of T3 with a T1 in the call to plus there. So that means that the T3 goes away completely. That was the point. So that allows us actually to keep pushing on this and reuse the fact that T4 and T2 are now the same. They do the same operation on the same input, so you can replace one with the other. And we end up having a simpler graph that looks like this, where you're doing less computations, and at the end we can generate code that looks something like this instead. This is very simple stuff. It just shows you how you run through the graph, run through the code, realize that certain things are the same, they are equal, and you just get rid of the redundant version of it. So the algorithm used to actually implement this thing is pretty simple at the high level. You just walk the Dominator tree, and you keep a set of live values, values that you've already computed. And if you find an instruction and you already have a live value in your set, you just pick that live value instead and replace the current instruction with that live one instead. And of course, you register these instructions in the set as you go. And the biggest thing is that you need to make sure that if you see something that has a side effect that could affect something in this set of values, you need to remove that from the set. So it's really just a walk through the Dominator tree where you keep track of which values are already computed and can be reused. So the control flow graph associated with the Dominator tree like this is still necessary when you do these operations, because when you walk the Dominator tree, you may have to kill, you may have to get rid of live values you computed for one branch based information in the control flow graph. So the example here is that if you get to the B2 basic block, you actually have to let that perhaps affect the live value set for the analysis of B3, because B3 can be reached through B2 in the control flow. So it's kind of complicated, but the net result is that we generate smaller code and more efficient code. One of the biggest things that we still have problems with is that we have a lack of knowledge in the generated output. So even when we propagated tons of types in the system, we still have this problem that the code that we can generate when we have no type information is a lot worse than the code that we can generate when we have it. So sometimes we feel like we can actually make a pretty good guess. Like if you're using something like a list, maybe we should just treat it as a list. If you're using something like a number, if you're adding them together, for instance, maybe we could just treat them as numbers. The only problem is that we could be wrong. So we try to guess based on inputs and how things are used, if they are, for instance, numbers. But when we're doing what we call speculative optimizations, we have to be aware that we're just guessing and we're not quite sure if we're right. So let me show you how that looks. If you have code like this that runs through an array, uses the x.length property, adds up everything in that, it would be really nice if we could optimize the access of the array elements of x and make use of the fast primitives for that. The problem is we don't know if x is an array. It could be a string. It could be something weird. We just don't know what it is. But the compiler we have still actually allows us to speculate and say, it would be fantastic if x was a JavaScript array at this point. So why don't we just try to compile it as if it was? So we end up generating code like this. The first thing that we do is we check if x is a JavaScript array. If it's not, we deal with that. But if it is a JavaScript array, which is the case from the first line down, essentially, we can just go ahead and do all the operations on that JavaScript array, knowing that it is a JavaScript array. And we can access the length, and we can access the array elements in a really fast way. We still have to check that the things we read from it are numbers, and we have to check that we're within bounds. But it's still much better than having to call arbitrary methods at this point. The problem is this first line that checks if x is a JavaScript array. It would be kind of neat if we could just throw an exception there and say, it looked like you were using this as a JavaScript array, and it really isn't, so maybe this is a bug in your code. The problem is that, well, it's actually not a problem, it's a feature. The nice thing is that people can write their Dart code and have objects that behave just like the built-in lists. And that needs to work too. So we have to generate a version of this sum method that works without the assumption that x is a JavaScript array. So what we generate is actually this. a separate method called the bailout version, which has some state that we use to actually enter the method in different places if that's necessary. And it has the environment, the live variables that we need to transfer from one to the other. In this case, it's just X. And here you have the slow case version of the code, which is what we would have been forced to generate if we didn't have the speculative optimizations in play. So what you see here is many more method calls to methods that try to compare if things are less than. You try to get the lengths by calling an accessor. You try to index into something by calling the index operator. Well, not the index operator, the index method. So this is just much slower. So we much prefer running in the optimized version of it. So we have to put this in to have proper Dart semantics, but we believe that that we will never use this method. So we really have to try to cut down the speculative optimizations in the system. So otherwise, we would generate too much code that we would never need. It's really hard to strike the right balance between optimizing too much and too little. We don't have enough information at this point. It's a sort of a static analysis thing that we think this might be used in one way or the other. So right now, we've cut it down to a point where we're only speculating about types for values that are used from within loops, where we can actually move certain checks outside the loop as a consequence. So if the speculative optimization we can show that it's good enough to actually move things out of loops, we'll do it. Otherwise, we'll try to not do it. We have some ideas on how to actually improve that a bit. So what if we actually just went ahead and generated speculative optimizations about all the types that we would want to optimize based on, and then took that resulting, too big code though, but just like put that out there and ran through it and profiled it. That would actually give us some insight into how the program is being used. And it would allow us to actually look at which of these bailout methods are actually being called. It would also allow us to look at which of the optimized methods that are being called and which ones are hot. So one neat way of doing this would actually be to speculatively optimize everything and then recompile with less speculation, where you only allow speculative optimizations in methods that were actually hot in their optimized version. So it's something we haven't implemented yet because the tool chain around having a profile guided optimization step is kind of complicated for our users. So, but it seems promising in the way of getting more information about what the program actually does at runtime. So one thing I want to say about dealing with control flow in the code, we would generate this SSA form, and it's kind of hard for us to take that form and compile it to nice-looking JavaScript. The examples I've shown you hopefully don't look too foreign, but it's actually kind of hard to translate a generic graph that has arbitrary jumps between basic blocks to something that looks like JavaScript. So what we've done is actually we've tried to keep the code structure from Dart in the SSA form we built, not mess too much with it, and just compile that to the same corresponding JavaScript control flow statements. It's not the ideal solution, perhaps, but it actually works pretty well. And it's just, there are certain optimizations on the control flow that we cannot do that way, but it works fine for data flow. So just to give you a feel for what that looks like, the kind of place where we have problems with this is where we have to introduce checks in places where the JavaScript syntax only allows expressions, essentially. So in this case, you have an index check that you want to inject in the condition of a for loop. It's kind of hard to do in an efficient way. So what we end up compiling this to is something where we cannot compile the for loop to a for loop. We compile it to a while loop with some breaks in there to try to escape that boundary. This is not as pretty. It's bigger code. It solves the problem in this case. But in general, being able to compile a for loop to a for loop and a while loop to a while loop is just nicer. So hopefully this gave you some insight into how the compiler is written and what kind of optimizations it does. What we focused on mainly is, in addition to runtime performance and correctness, it's really the code side that has improved the most since our first release. What we're seeing right now is that small examples actually do compile to small pieces of JavaScript output, So it's not the case anymore that you will get megabytes of JavaScript emitted for a small hello world example. One thing that we sometimes do see, though, is that people write an application that depends on a lot of libraries that it pulls in through imports. So if your application translates to sizable chunks of JavaScript, it might be because you're importing and using a lot of code sort of transitively. We still have more work to do in this area, and we'll continue to push on this, but it's getting much better, and it's kind of nice now. One thing that we haven't implemented fully yet is support for generating minified output, which is very common in the JavaScript world, where you get this slightly obfuscated and minified version of your JavaScript output that's very well designed for transmitting across the wire. It's essentially just a rewrite phase that cuts down on the use identifiers in your code and makes them as small and short as possible. So you can already use that and experiment with it now through the minify option, but you should expect it to be getting a lot better over the next weeks and months. So I don't know if this is actually something you can see at the back here. This is a slide that shows you our internal performance tracking site. So this is a subset of the benchmark that we run. I just wanted to show you that we do care about performance, and we track it every day. If you really want to make a system fast, you need to measure performance in every check-in, essentially, and we do that. We measure ourselves against V8 because we have a lot of familiarity with the code it generates. So what you see here is actually on the very right, you see for all the benchmarks that I've listed here, you see how fast we are compared to V8. So the last column, the very right column, is Dart-to-JS. So that is how fast are we, how fast is the generated JavaScript code that we emit compared to just handwritten JavaScript code. We still have some work to do. We're at around 78% of the performance of pure JavaScript code. But you have to pay keep in mind that this actually includes all the extra checks that we put in there that might help you catch your bugs before they go to production. So we are generating code that is not as efficient as native handwritten JavaScript in all cases yet, but we're improving a lot. You can also see that the native Dart VM, which is the second last column here, is actually doing better than V8 already. It's something that we will keep on pushing on, but it's nice to see that because of the semantics of Dart, it's a simpler language to implement efficiently. We're already now, even before the first sort of real Dart release, we're already 20% faster than V8, and we certainly expect to improve that number going forward. So expect more on the performance front, always. So conclusions are very simple. You should write your web apps in Dart, and you should compile them to JavaScript if you need a compatibility story with the modern browsers. You can be more productive if you have a good tool chain that goes from editing and a good compiler to generate these things for you. And you can let us worry about some of the low-level optimization, so you don't have to argue with your coworkers about all these low-level tricks and things you need to worry about in JavaScript. So last thing is that we really want to keep improving the web platform. We really believe that the web is in need for better support for programming in the large. In particular on mobile, we see that application startup for big web apps is still a problem. It's something we certainly want to solve, and we want to give you more predictable and better runtime performance. And as you've already seen, we're getting very close on the Dart-to-JS front with native JavaScript performance, and on the VM front, it's already better. So that was all I had. So I'm very, very open to any kind of questions you guys may have about the technology or Dart. Okay, so the first question is about debugging and using JavaScript libraries. So debugging first. So our debugging story is really that when you're running with the Dart VM, it's fairly simple. You have a debugger API for the VM, and you can use that as if you were running any other native VM solution. For the generated JavaScript code, what we produce is a source map on the side that tells the developer tools that you're hooking it up to where essentially it gives you like a mapping from the generated output back into your source code. So you can do like single stepping through your source code even though you're running the JavaScript code. So we're getting a lot of help from the fact that others have already generated this source mapping format. So we use that. The second part of your question was around JavaScript integration and interoperability with existing JavaScript libraries. It's a really hard problem. And it's something that we've talked a lot about, different approaches to. And the biggest problem we have is really that we want something that runs well on the native Dart VM and on the translated version that translates to JavaScript. So we want a solution where you can take a piece of JavaScript code and interact with it in the same way, no matter if you end up running on the Dart VM or if you're in a translated version. So what we come up with so far is a sort of limited way of synchronously calling essentially external functions, external JavaScript functions, and then doing some serialization across the boundary between these, the JavaScript world and the Dart world. So it does mean that essentially doing this integration is a bit more cumbersome than just calling JavaScript functions and getting stuff back, but we have to do some checking on the boundary to make sure that the two worlds are in a consistent format, and you don't get a lot of pointers to raw native JavaScript objects sort of embedded in all your Dart objects. So it's doable. It's getting easier and easier, but it's still something where it takes some amount of work to integrate with an external library. One thing that I always like to ask is what kind of libraries would you like to integrate with? Because usually there's like a bunch of very, very important JavaScript libraries that people really would like to see, like jQuery and mobile jQuery and whatnot. But the list is very short. So if you have something that you would like to see integrated, we would like to know about it. So the question is, given that we, as Google, control V8, have we given into the temptation of adding stuff to V8 that will allow us to generate better JavaScript and run it faster on V8? Yeah, so far we haven't added anything to V8 as a result of our Dart stuff, except for some missing optimizations that we found. For instance, V8 was not particularly good at dealing with unsigned 32-bit values. It only dealt with 31 bits, and we had some benchmarks where it really, really mattered. So there is some feedback coming from the Dart team to the V8 team on particular things that are not performing as well in V8 as on maybe other JavaScript engines, so there are optimization opportunities. But we really only want to put stuff in V8 that generally makes sense for JavaScript programs. So our style here is really to try to generate JavaScript code that runs well on all the modern browsers, and it doesn't really buy as much to make that run 10% faster on V8 alone. So far it hasn't been something that has made sense to us. I understand I mean, you could be tempted to do it, but we wouldn't win anything by doing it, essentially. And to be honest, the places where we have V8 are also the places where we are more likely to have the Dart VM. So I don't think it actually is a terribly good idea, except for finding bottlenecks and existing performance things that can be fixed. So the question is, did we consider adding a flag for enforcing stricter typing to be able to generate better code? So we actually haven't considered that at all, because we really feel like Dart is a dynamic platform, and we really want it to be used as a dynamic platform. So this notion that you don't have to write types everywhere to get a correct and efficient program out is very important to us. So no, that hasn't really come up as something that we wanted to do. Some people have asked us if we wanted to maybe trust type annotations when they're there, to generate code just based on the type annotation, just assume that they're correct. So far we haven't done it. Clearly in some cases that would allow programmers to express to us that certain things are probably likely to be numbers or whatnot, but we haven't really taken that step. Mostly because, as it is right now, we kind of like to have that extra pressure put on us to deliver high performance without changing the meaning of the static type annotations that people have put in. We really want to keep that as a documentation of intent from the programmer, not some low-level optimization trick. So the question is, have any other browser vendors shown any interest in implementing a Dart VM? I actually don't know if anyone has shown. I don't think we've seen any public support for the Dart VM across other browsers. I think it's still very early. The Dart VM is maturing. As you can see, the performance is getting there. There's still a lot of headroom. We can do much better. I think it's on our table to try to demonstrate how much that affects what you can build on the web when it comes to application startup and peak performance. And once we have that, I think it's very for us, it's very hard to control what will happen from that point forward, but of course, we hope that people will find that technology to be so compelling and interesting that they want to use it too. So the question is if when we switch isolates, you're just assigning to this dollar variable, and if there's any code sharing behind the scenes between different isolates. So right now, there is actually 2 different versions of creating an isolate. Either you're running you're spawning another isolate based on your own source code, in which case we do the code sharing. But it's also possible to spawn an isolate from a URI where you don't know what you're spawning, in which case we don't actually try to do any code sharing. So it's actually up to the programmer to request one or the other. And clearly, if you're spawning based on your own source code, it makes perfect sense to do more code sharing, and there are no weird versioning conflicts that can arise because you know you're guaranteed to be running the same source code. So that's a nice place to be, and that's the place where people usually end up being when they just want to use isolates for carving up their application in more bits and pieces, but also either getting some of the security benefits or just the concurrency benefits of having. So actually what we do is we have an isolate object which is actually created through a JavaScript function that has tons of properties. So we just use the same constructor for creating the next one. So essentially it's a JavaScript object that has, it looks more or less like you have a JavaScript class as well. We just instantiate once for every isolate. So it's fairly lightweight that way. And the idea is that we want to allow people to either run them as web workers or not, depending on what they really need. Sometimes if they have a need for DOM access from multiple isolates, the only thing you really gain from having multiple isolates is this carving up your application in multiple pieces, and you also gain an extra global namespace essentially. So for all the static state, you get a new copy of all that. All the static variables are just split that way, which is good for some things. I think we have time for one more question, but I think we're running out of time. Yeah, one more question. So the question is, do we have libraries for accessing the DOM APIs and databases and things like that? So clearly these things are being built as we speak. On the server side, there are many different databases that you can access, and we have some interfaces for some of them built by people in the Dart community. On the, when embedded into the browser, we have the full range of DOM and HTML APIs available to us, and we do have access to them through the Dart::HTML library, which is just a simple way for you to write code that accesses the DOM through Dart. So yeah, there's full support for that. So that goes for all the index DBs and all those things that are in the browser. So we're not trying to limit your access to the DOM-based APIs. We just want to give them a new, saner language to write in and still be able to use the browser technology. So we're running out of time. Thanks a lot for spending time with me today, and I hope to see more of you in here for the remaining talks in the JavaScript track.